Hello students, and welcome to this class where we are going to talk about partial differential equations. Now, first of all, this is the first such lecture where we are going to talk about what PDEs are. So in short, we call it a PDE, right? Partial differential equation. Now, first of all, we are trying to give you some idea of where exactly, what exactly is a PDE. Okay, so first of all, to understand that, we have to go through what is an ordinary differential equation. Okay, this I am quite sure you guys already know, but still, let me give you a definition of an ODE, and from there we are going to motivate what a PDE is. So let's say you have in this thing we are always going to take AB. AB is the first interval I1. Okay, I1 we are going to call it as AB, and you see, let's take a function U. Okay, from I to R, let's say. Yeah, this is an unknown function. This is an unknown function. Okay, whether the function is continuous, not continuous, we don't know. Just as given that this is an unknown function. Okay, unknown function. And so consider the following relation. So essentially we are going to look at a relation. Okay, following relation. What is the relation? So basically this is a function of x. I am taking it from I1. Okay, and then you have u is u of x, that is. Okay, and then u of x is in R. You see, u of x is in R, and then u prime of x, of course. No, I'm not writing the x part always the time, so we write that f of x, u and u prime. Okay, and let's say this is equals to 0. Yeah, and where we'll define f, where f is defined from, see, the first variable is I is varying in I1, right? So I1 times the x, the first variable is x is varying in I1, and the next variable is u. So where is u varying? U is varying in R. See, x is varying in AB, so u of x is in R. So it is I1 cross R cross the third variable u prime, that is u prime of x. Again, that is also in R, right? So f from I1 cross R to R, that's a given function, is a given function. Given, and for now let's just assume that this is a smooth function. Okay, so we call, now you see, let's call this as the equation 1. Okay, so the relation f of x u prime equals to 0, this is the relation. See, for something like this to work out, actually, you see, you need at least u prime should exist at all points x, otherwise this does not make sense. Okay, so we will assume that it is a unknown smooth function. Smooth means at least C1. So whenever in the context of PDE I am saying smooth, it is at least C1. In some context it will be C2, depends on what order equation you are talking about, but generally it is C1 or C2. In this case it is C1. C1 means it is continuously differentiable. Okay, right. So this is a given function. Now 1 is called, so 1 at this level is just a relation. Yes. Okay, so we will call that relation an ODE if, so essentially f with respect to u prime. Okay, so u prime, if you want, without getting confused, let's just write it as z. Okay, fz of x, y and z, this thing should not be 0. So basically f depends on the third variable. See, if f is independent of the third variable, right? Third variable is what? U prime. So if f is independent of u prime, what happens is basically the relation does not contain any term of u prime, right? Yes, it does not contain any term of u prime. So basically, if there is no derivative term involved, then the equation cannot be an ordinary differential equation. There is no derivative, so it can't be a differential equation. It is some sort of equation, but not a differential equation. Okay, so one is called an ODE if fz at the point x, y, z is not equals to 0, where we'll write u, this variable u. Okay, so basically u of x, if you want, you can write it like this. U will call it as y, and u prime will call it as z. Okay, it's just a nomenclature, we are just calling it names. Okay, so essentially, as I told you, this means that with respect to the third variable, see, with respect to first variable, second variable, it may be 0, but with respect to the third variable, we should not be 0. Okay, right? So as an example, let's just understand what this means. So basically you have a relation. First of all, you have a relation, right, which is given by f of x u prime equals to 0, and that relation we will call it an ODE. If with respect to the third variable, it has to be non-zero. In fact, we call it not just an ODE, we call it a first order ODE. First order ODE. Why first order? Because the highest order term which is involved in the equation is u prime. You see, u prime. So basically it's first order. Now let's say you can also talk about something like this: f of x u prime u double prime equals to 0. You can also do that. Okay. And in that case, we call it a second order equation. Okay. It's called a second order. Clear? Of course, for this equation to be called second order, what do you need? You need, let's say this variable is called w. If w with respect to x, y, z and w is non-zero, you understand, then we'll call it a second order. So similarly, third order also you can define something like this. I hope this is clear. Yeah. Okay. So this is called a first order ODE. Okay. Let's take some examples and see what I mean by this. See, let's say if I define f of x, y, z to be just x. Okay. Now if that is equals to 0, that does not give you an ODE, not an ODE. Okay. An ODE. X equals to 0. What does that give? Nothing, right? Okay. And similarly, even if it is xy, let's say, equals to 0. So basically, if you write it in terms of equation, it becomes x times u equals to 0. U is the equation, the unknown function, and x is just a variable. So x times u is not equals to 0. Again, not an ODE. It's a relation, of course, relation between x and the function u, but not an ODE. Okay. So you understand that these are not ODEs, because you see, if you can look at it, see why it is not an ODE. Let's say x or x, I don't know, maybe let's put it at xy. If it is not an ODE, because if you are taking the derivative with respect to z, capital F, see, that is going to be 0. Okay. So this relation is not satisfied, hence not an ODE, not an ODE. Okay. So this is just a case. Now, what about the something else? Let's say that when is it an ODE? Let's say if you have a relation like this, f of x, y, z is given by, how do I put it? Maybe let's just put it like z plus, I don't know, maybe y, x, y, let's say. Yeah. Now, is this an ODE? Let's just understand this. See, fz. Yeah. What is fz? This is going to be 1, which is non-zero. Yes. So that is definitely an ODE. So this is definitely an ODE. Okay. So how does this ODE looks like? It's an ODE, fine. But I mean, you definitely did not, saw an ODE looks like z plus xy, right? So what does it look like? This is, you see, this is in a short form, right? If you want to put it in terms of a function, this z is what? U prime. So u prime plus x times y is u. X remains x and y is u. This is equals to 0. Now you see, this is an ODE, right? So please understand, ODE which you have seen, that is with respect to an unknown function. Yes, this is a relation capital F. This will be given to you. Yeah, it's a given smooth function. Is it okay? So u prime plus xu equals to 0, that's an ODE, no issues here. Okay. And similarly, you can also talk about second order ODE as an example. Let's say, let's take one example of a second order in this case. I hope, you are understanding, and in any case, if you want, you can pause the video and then look at an example yourself. Okay. So let's say f of x u prime u double prime equals to, I'm defining a new equation. Yeah. And what is it? Let's say I will define it like u double prime plus 1. Okay. I can define it like this. So that is f. Now, is it a second order ODE? To check that, I have to do f of, so basically if you want to write it at f of, this is y, this is z and this is w, then it is f of x, y, z, w, you can write it as w plus 1, right? And that will imply f of, with respect to w, you have to do, it is second order, so with respect to the highest order, so fw at the point x, y, z and w, this you can see that this is going to be 1, which is again not equals to 0. So this is a second order equation. Okay. Of course, you can put a power also, let's say square also, no issues there. Then it will be w square and it will be 2 times w. Okay. Again, that is not 0. Yeah. Not for all w basically. Yeah. So essentially, this is again a ODE. And it's a second order ODE. Why we are calling second order? Because the highest order term which is involved here is 2, the derivative, the highest order derivative, that is 2. So it's a second order ODE. And similarly, you can define the higher order. Okay, so that's an ODE. See, why ODE? Because the derivative which is involved is ordinary, just one derivative. Okay, so now let's understand what's a PDE. Okay, so PDE. Now, see, PDE is nothing but a generalization of ODE. So essentially, let's say I talk about this, a new rectangle I. This is what I am defining, a rectangle AB cross CD. It doesn't have to be rectangle. I am just defining it for a sake of understanding. Is it okay? It can be any domain, and I am doing it for n equals to 2, and let n equals to 2. Okay, why n equals to 2? Because if you understand n equals to 2, you can do it for n equals to 3 or higher dimensions also. Okay, so exactly the same thing. It does not really matter. So let me just stick with n equals to 2 here. Okay, so I is a rectangle. What is this rectangle? AB cross CD. So let's say this is A, and this is B, and let's say this is C, and this is D. Okay, so this particular rectangle we are talking about, we are interested in this rectangle in R2. Okay, so this is your I. Okay, and our dimension is U, and you have a function U. Okay, this is your unknown function, which is given by I, which is defined from I to R, is a smooth unknown function. Okay, smooth unknown function, why we are taking? Because we have to talk about derivatives of this function. Okay, function. Now you see, the thing is, the function is a two variable function, right? X and y, two variable function. So u is a two variable function. Now if you want to talk about the derivative of u, so basically what is the derivative of u? It is given by gradient of u at the point x comma y. Okay, and what is it? That is, as we already talked about, it is ux and uy. I hope you remember that. Okay, so you see all these things. So basically now when we call this thing as a PDE, if so, consider this relation, similar sort of thing as ODE. Yeah? Consider the relation, and what is the relation here? Again, I am sticking with the first order. Okay, capital F of xy. So initially it was our just an x, you see, because there was one variable. Here there are two variables, x and y. Now what is the next thing? You have to talk about u of x and u prime of x. Okay, so what is u of x here? Nothing, u of xy. Okay, so I'm not writing u of xy, I'm just writing, sticking with u. Okay, and then you have the derivative of u, which is gradient of u. So of course you can write it as gradient of u, that's not an issue, or you can break it up and you can write it as ux and uy. No issues. You can do it both ways. So let's say this is equals to 0. So let's call this as 2. Consider this relation 2. Where what is f? F is a given function. And where is it defined? First of all, let's understand x. First of all, the first variable x is in AB. So it is AB cross, the second variable is in y. So it is CD. Y is in CD, right? And then u. What is u of xy? See, this u is nothing but u of xy. So given an xy, we are looking at u of xy. I don't want to write it because it will become much bigger. So I'm just writing at u. So u is a function from I to R. Yeah? So u is taking a two variable thing and putting it in R. So u of xy is in R. So this is in R. And similarly, ux and uy will also be in R. So this is a f is this function to R is a given smooth function. So this function will be given to you, smooth function. Okay, smooth function. So let's just consider that this is a relation which is given to us. So in this, up till this level, this is just a relation, nothing special. Okay, now you see, if, okay, f with respect to, so let's just call it like this, ux, or f with respect to uy, okay, is non-zero, okay, then we call one as a first order PDE. Is it okay? So initially it was first order ODE, here it is first order PDE. Again, you understand that why we need this particular non-zero thing, because if both are 0, so let's say if fx and fy, so basically if these both f with respect to ux and f with respect to uy, so I'm writing ux, uy, you can just write it in terms of variables. So basically what I mean is this, you can write this as f of x, y, let's say u is z and ux is w, and okay, ux is I don't know, maybe you want to put it pq, let's just put it pq, Let's say that is equals to 0. That's the equation. Huh? So here z is u, p is ux, and q is uy. Let's just assume that. Okay. Now, if you assume that, you see f with respect to p, yeah, let's say this is equals to f with respect to q, which is equals to 0. Let. If this is equals to 0, you understand, then that will imply that f of x, y, z, p, q will be just a function, some function of x, y, and z. So it is independent of p and q, yeah, and not an PD. Because if you have to be a PD, it should involve some partial derivatives. But since it is devoid of such partial derivatives p and q, so it's not a PD. Okay. So let's look at an example now. Let's look at an example. First of all, let's look at an example of a f where it is not giving a PD. So let's say f of x, y, z, ux, and uy. This function is given by I don't know, maybe let me put it as x plus yz, some function. You can just make it up, doesn't matter. So let's say this is equals to 0. That's relation given, and when I'm putting it equals to 0, that is the total relation which is we have. So the function itself, the capital F, which is given to us, this is given function. Okay, f of x, y, z, ux, uy is x plus yz. It can be the case, right? And then that is equals to 0. So is it a PD? Not a PD. Not a PD. Why it is not a PD? Because you see, if you are taking f with respect to ux or uy, so ux, uy, we can write it as p and we can write it as q. So f with respect to p and or f with respect to q, they are all going to be 0, right? So not a PD. Okay. So now let's look at things which are PD. So what are the important PDs here? So one very, very important PD is this. So let me, for now, let's just write it as ZPQ. Okay. So f of x, y, z, pq. This is the relation, and I will give you the function which is given here. So let's say this is p plus q. Yeah, very simple function. It is a smooth function, mind you. It's just add. I mean, we are just taking two variables, the last two variables, and just adding it. So very nice function, right? Okay. I mean, if you want, you can just add some constants also. Let's say alpha and beta times q, and alpha beta is in r. Some constant. Alpha can be 1, beta can be 5, something. Yeah. Now you see, with respect to p or with respect to q, this is not going to be 0. Okay, both are not going to be 0. You can easily check that. So check that f equals to 0 is indeed a PDE. Indeed a PDE. So how do you check? You just check FP and FP. Now, okay, fine. It's a PDE. But how does it look like? See, it looks like this. Alpha times ux plus beta times uy equals to 0. Okay, this type of equation, this is a first order equation. Why first order? Because it only involves the first derivatives. Okay, the first order derivatives. So this is called the transport equation. Okay, sorry, not transport. This is called a transport equation. I hope this is clear. So this is a very, very important example of a PD. Let's just look at some more examples. Let's just understand in a better way. F of x, y, z, p, q. Okay, let us put it like this. Z, p plus q. Let's just, okay, and this is the function given to us, yes, and let's say if this is equals to 0, you do realize f with respect to p and f with respect to q is not going to be 0. At least one of them is not 0. So basically this is R and PD. And how what sort of PD is it? So basically the original form, this is the original form, right? The original form will look like this. This is Z is what? U, right? P is ux, ux plus uy equals to 0. Okay, this is also a type of PD which generally in some cases we call it a Burger's equation. Okay, so in some cases we call it a Burger's equation. So similarly, you can make up a lot of different PDs. Absolutely no issues here. Okay, so that's the first order of PDE. Now let's understand that can we define a second order PDE? Yes, of course we can. Yes. So I am not going to define it formally, but you do realize that if you have to define something like this, what are the variables that is involved? Let's just understand this. See, u is from in a two variable function on to r, right? So therefore, if you want to talk about the second derivative, you have what are the terms involved here? Of course, u prime. What is u prime? It is ux and uy, the first order. And then you have second order terms. What are the second order? So two variables are there. So all possible combinations uxx, uxy, and uyy. Of course, uyx is also there, but since we are taking u to be smooth, so let's take it to be smooth. Smooth means here it is at least C2. So if it is C2, then uxy and uyx, these two are basically same. Okay, so in this case it will be what sort of function? So we are looking at a function f, which is a function of two variable function of x, y, u, ux, uy, uxx, uyy, and then u of xy equals to 0. Okay, here we are assuming that u is at least twice continuously differentiable. So this is the equality of mixed derivative, which we also discussed in the first lecture, if you remember. Okay, and so this is basically is the given relation. And you do realize that for this to be a second order equation, so this is called a second order ODE. So let's just call it a 3. So 3 is a second order PDE, if at least with respect to these three variables, at least one of them has to be non-zero. Is it okay? So I don't know how many, how am I supposed to put variables here? Let's just call it these variables alpha 1, alpha 2 and alpha 3. Yeah. So basically f with respect to alpha 1 or f with respect to alpha 2 or f with respect to alpha 3 has to be non-zero. Yes, very simple. I hope you understood. So as an example, let's just take very important examples. So let's say the first f which we are talking about. So f of x, y, u, let me put it as gradient u. This ux and uy, I am putting it as gradient u, and these three terms I am just writing. This is a shorthand version. Please don't take literally. This is a shorthand version. I am writing as d2u. Okay, so because I don't want to write it all the time. So these, let's just call it as the given function. Let's just put it as alpha 1 plus alpha 2. So basically uxx plus uyy. Let's just keep it this way. Okay, so this you do realize that I mean f with respect to alpha 1 or f with respect to alpha 2 is definitely not going to be 0. So this is an PDE. So this equals to 0, and this PDE is called the harmonic equation. Okay, it's called a harmonic equation. Okay, now so basically any solution of this equation is called a harmonic function. So in that sense, it's called a harmonic equation. Okay, right. Let's say I define a new function f of x, y, u, gradient u, and d2u. Let's just define a new one. So here I will define it in this way. uxx minus uy equals to 0. Okay, this is called the heat equation. Of course, heat equation, you have seen some time variable t is there, but here I am just replacing that t with y. That's all. Okay, so uxx minus uy equals to 0. Of course, constants can be there. You can accommodate those constants, but here I am just keeping it simple. Okay, right. Let's look at another example. F of x, y, u, gradient u, and d2u. So you understand d2u contains all possible second derivatives. So that is why this part is there. So these, let's say I write it as uxx minus uyy equals to 0. Again, you can easily check that this is going to be a second order PDE because either one of them is not going to be, both of them are basically non-zero. Okay, this equation is called a wave equation. Very important. Okay. See, this harmonic equation is also called a Laplace equation. Okay, it depends on whom you are asking, but generally, I mean, generally speaking, people call it a Laplace equation. You can also call it a harmonic equation. No issues here. Okay, and the thing is, this is a heat equation, and the third one here is a wave equation. Okay, so you see, in this particular course, what we are going to do is essentially we are going to study this sort of equations. Basically, this equation, transport equation, Burger's equation, and then these three sort of equation: Laplace, wave, and heat. Is it okay? Those are the three equations which you are going to study, and I will show you why we are basically studying these three particular equations. Okay, right. So now that we have the definition in order, what we are going to do is, see, in PDE or ODE, we always put this term, right? That there is a solution. But what is the understanding? What do we mean by a solution? So basically, solution to a PDE. Let's just understand that. Solution to a PDE. What does that mean? Let's just understand that. Okay. So let's say U is said to be, so for now I'm just sticking with two variable, dimension is 2, and first order, okay, is said to be a solution. So I'm taking this, otherwise you can take it to be higher order also, no issues, exactly the same idea works. So U is said to be a solution of, let's say, f of x, y, u and gradient u. First order, first order I'm just taking, and this is an PDE I'm assuming. So basically, with respect to this variable, it cannot be 0. Okay. So U is said to be a solution of this equation if two conditions. See, for this equation, so let's say f is generally continuous function, right? So with respect to this variable, you are talking about derivatives. For this to be a PDE, with respect to this variable, we are talking about derivatives. So basically, we are assuming that at least f is such that the derivative with respect to this third, the last variable exists. Okay, and whenever we are saying derivative with respect to, there is another thing. This variable also contains derivative. You see, gradient of u we are talking about, which is nothing but ux and uy, right? And you see, for ux and uy to exist, so basically, if this either one of them does not exist, this does not make any sense. You understand? So for making sense of this particular thing, we are assuming that both ux and uy exist. So if A, both ux and uy exists for all x, exist for all xy in I, and moreover, you see, just for, I mean, the sake of understanding, please understand this thing. Yeah, let me give you an idea. So let's say this equation we are talking about, ux plus u is equals to 0. Let's just stick with a very simple equation, ux plus u equals to 0. So you see, the thing is, for this, I mean, this is a relation, right? What is the relation? The relation is f of x, y, z equals to u plus ux. So that's the relation, and you do realize that's an ODE, a PDE, sorry. So you see, what I'm trying to suggest here is this. I am saying that there is a solution of this equation. So basically, it means that there is a u which satisfies this particular relation. So if it has to satisfy the relation, ux has to exist. Yes, you see, and ux has to be equals to minus u. You see, because ux plus u equals to 0, so ux has to be equals to minus u. Yes. Okay. So we are looking for a function u such that the derivative with respect to x exists, and that derivative will be equals to minus of the function. Is it okay? So here, at the very least, ux must exist. Okay. Now, is it enough? No, it's not enough. See, ux must exist and it should be equals to minus u. So essentially, we are basically talking about, let's say, without, I mean, not going much into details, let us just stick with this, that more or less, you see, of course, there are functions which are not continuous for which ux exists. That's not an issue. But the thing is, we are assuming, I mean, for reality purposes, for the purposes of working properly, we are assuming that u is a continuous function. So basically, minus u will also be a continuous function, and in that case, ux will also be a continuous function. Yes. So basically, ux exists and is continuous. Okay, and similarly, so this is an example, but generally speaking, in many problems, we will have both ux and uy has to exist. Okay, so they both will exist and they will have to be continuous. So basically, both exist, and for just for safety purposes, it doesn't have to be continuous all the time. But for now, just for this is our notation, we are assuming that this is going to be both exist and they are continuous. I hope this is clear. See, continuity is not a requirement. It may not be required. But the thing is, we are assuming it just for safety purposes. We are saying that we need some function which has at least some regularity. So, such a function, we call it a C1 function, as you already know. This is called a C1 function. What are C1 functions? So, basically, both derivatives exist and they have to be continuous. Okay. And B, what do you need? We need u to satisfy the equation for all xy. So basically, u should satisfy u. So this is this relation is true. F of x y, u of x y, gradient u of x comma y. This has to be 0 for all xy in I. Yeah. So if it satisfies something like this, then the relation has to hold for all xy. You can't say that there are like some xy's for which it is holding, some xy it is does not hold. Okay. So we are looking for a smooth function such that for all xy this relation holds, and then we call such a function as a solution. Please remember this. This is something in general PDE framework we call it a classical solution. There are a lot of different ideas of solution, many different things. Weak solution, strong solution. So we are not going to talk about this. This is a solution for us. We call it a classical solution or just a solution. Okay. This is also called a classical solution. Classical solution. Okay. Now, so that is what we understand by a solution. So let's just take up an example and see what it means. So essentially, let's take a very, very simple PDE, right? So let's say u x evaluated at the point x comma y. Let's say that is equals to 0. Is it okay? Now, if that is the case, see what it is saying is this: u with respect to x is 0. It means that u will not contain any term containing x. You understand? U should not contain a term which has x. Otherwise, ux can't be 0, right? Okay. So basically, it means that u of xy should only be a function of y, phi of y for phi in C1. C1 why we are taking? Because we are assuming that it is at least smooth. Okay, smooth means continuously differentiable, as we have already taken. So basically, u of xy equals to phi of y for phi in C1. We may not take C1. You understand that, right? It may not happen that phi is C1. Please understand that. So basically, this is a important question for you. Construct phi which is not C1 but satisfies the equation. It does happen, satisfies the equation. Okay. So you can construct that such a thing. But the thing is, please remember this, that we will not consider as our solution, because for that to be a solution, we need continuity of both the variables with respect to both variables. Okay. So u of xy has to be phi of y plus some constant k, and k is in R. Okay. Why this is true? Because you see, if you are taking u of x, so if u is this, what is u of x? It is phi with respect to x, which is going to be 0 because phi is just a function of y. And then there is a constant. Constant is also going to be 0. So that is equals to 0. So you see this equation is satisfied. Okay. So ux equals to 0 is satisfied. I hope this is clear. Okay. So what is the solution of this equation? The solution of this PDE is phi of y plus some k. So that's some general solution. Okay. Right. So why are we saying solution? See, for any xy, this particular thing, phi of y plus k, for any xy, this relation holds. This relation holds. That is true. Another thing, you see, and this k can be anything. It can be 1, it can be 5, it can be 9, doesn't really matter. It does hold. Okay. Another thing, that you see why we need this phi to be C1, because if phi is not C1, then U is not C1, and if U is not C1, then this does not satisfy this particular condition. Hence, it is not a solution. So this is a solution where phi is C1. Please understand this and write it like so. Okay, right. So this is a general solution. What do I mean by general solution? So now let's come to the point of general solution. General solution. So what is a general solution? A general solution to a PD solution to a PD2, PD which is given by 2, is a form of all possible solutions. So basically you take all possible solutions of some equation, put it together, and we'll call it a general solution. And what happens is, when this general solution becomes a particular solution, so in this case this is a general solution. See, phi is general. Phi can be anything, right, as long as it is continuously differentiable. And k can be anything. K can be 1, k can be 5, k can be 9, doesn't matter. So k can be anything. And now we have something called a particular solution. So what is a particular solution? So this is, as the name suggests, is very particular. So basically this is a general solution plus a data which is given at some line or some region. You understand? Okay. So basically, let's say the particular solution is a general solution. We can call it as this, a general solution with some data. General solution with sufficient data. Okay, let's just put it this way. Sufficient data. Okay. Now, so you understand what I'm trying to say, right? So basically, think of your ODE. If you understand, then exactly the same thing here. So basically, in this case, you see, in some domain, let's say in this domain, UX is 0. Yeah. So essentially, there are many different functions for which that happens, because any function of the form phi y plus k will satisfy that. But the thing is, now what I am saying is, you see, let's say there is a part of the domain, this part, where u is equals to, let's say, I don't know, maybe let's put u equals to 0. Then if I am asking how many functions are there, those functions will be a particular solution in this case. Okay. So it particular means it passes through some particular region. That's the point. So you can put it this way: it satisfies some particular sufficient data, okay, or it passes through some particular region. You can also call it that. I hope this is clear to you. Now, it may be unique, it may not be unique. The particular, see, general solution, of course, is not a unique solution. There are infinite solutions that you understand. Now, particular solutions also, it may not happen that the particular solution is unique. It may not happen. Okay, it may be there are like millions, billions of solutions. We don't know that. Okay, so anything can happen. But the thing is, particular solution is some solution. We are looking for solutions which satisfies a particular set of initial data. Okay, the solutions which satisfies a particular set of initial data. I hope this is clear. Okay, so whatever initial data is given here, I'm just giving you an example. Okay, so that's the idea of general solution and a particular solution. Okay, now let us understand some more. So now there is a very important concept of well-posedness of a PDE. Okay, so essentially the similar sort of thing in a ODE also is there. Well-posedness of a PDE. What does that mean? So let's say 2, the PDE2, if you remember, f of x, y, this PDE. Where is it? I just wrote, yeah, this one. If you want, you can, no, this is 3, this is 2, the first order. You can talk about 3 also, it's not a problem. So any PDE, basically here it is first order, in other cases it is second order also, it's not a problem. Okay, in this case it is second order. Okay, right. So okay, so 2, the PDE2 is called well-posed if A, the first thing is there exists, I will put it this way, there exists a solution. Okay, solution in which sense? Solution, this sense. You see, this sort of function has to exist, at least one, at least one. Okay, so the first condition, now both, all the condition has to be satisfied for the equation to be well posed. Okay, this is the first condition, there exists a solution, at least one solution. A solution, let me put it this way, there exists at least one solution, at least, very important, one solution. Okay, and the second condition is there, if there exists a solution, so the solution has to be unique. So we can put it this way, the solution has to be unique, Okay, so for example, let's say this equation, yeah, there is at least one solution. Yes, it is there. Is it unique? Of course not. So this equation from the very beginning is not well-posed equation. We call it a ill-posed equation. Okay. So first of all, it has to have a solution, and then the solution which you are got, we don't care at this moment how you got it, but if you have got some solution, that has to be unique. And then the third part is, for small change of initial data, for a small change of initial data, so it can be boundary data also. I mean, initial data, I mean that whatever data is given, huh? So maybe I can put it this way, for small change of data, the solution changes proportionally. So what do I mean by this? See, the thing is, what exactly means, you have to put some mathematical context here. So basically, think of it like this. See, first of all, let's say, what does a PDE do? Let's just understand that. A PDE, essentially, you are doing some, modeling or something. You are trying to model a situation, and when you do the mathematics, what happens is, it actually gives you some equation which basically turns out to be a PDE. Okay, now let's say that first of all, you need to know that. So think of it like this. Let's say there is a room, right? There's a room. This is the room, huh? Or maybe I can build a new, better room. Maybe I can do it like this. So let's say there's a room like this, square room. Okay, and there is an AC, and let's say all the doors and windows, everything is closed. So this is an AC, and this room, initially there is some temperature, and then the AC is blowing some cold air in this room, and then we want to see what is the heat distribution in this room. Let's say after an hour, after 2 hours, we want to see, let's say, this point. So initially, the whole temperature of the whole room, basically you can think of it as homogeneous. The initial temperature at T equals to, let's say T equals to 0, when the AC started, the initial temperature at this point, the point is given by, let's say, X and Y. The temperature is given by, let's say, U of XY, and 0 is time equals T equals to 0. Let's say this is given to be, I don't know, maybe 30 degrees or 35 degrees, let's say. Okay, now the thing is this, let's say that at T equals to 1, means after 1 hour, I want to see what is the temperature. So basically, we want to see what is F of U of XY1. So the thing is this, you see, U is something like this. It actually measures the temperature at a point and a given time. You understand? Same point, only here in this case it is the same point, but the time is changing. The point can also change. So basically, you model something like this. Okay. Now think of it like this. Let's say, if you want to talk about this diffusion kind of thing, heat diffusion, you have to talk about heat equations. We will talk about it later. Don't worry about it right now. What we want to do is this. Let's say that there is some equation which actually governs this whole phenomena, how heat is diffusing. Okay. The point is this. If you solve that equation, you want to find U, right? Because once you find a U, you just put X, Y, and T, and you can get this value. You can get what the temperature is at that time and at that point. You understand? Okay, so we want a U. Now the thing is, so first of all, we want at least one U, because otherwise you can't, if you can't find a U, there is no point doing anything of this, right? So at least one U. Now the thing is, the solution has to be unique. So see, the temperature distribution has to be unique. You can't say that at one point, let's say this point, if you are measuring temperature, if there are two different U's, then there are two different temperatures at the same time at the same place. Okay? That same time T and at the same XY, you cannot have two different temperatures, right? So you do realize that the uniqueness is very, very important. Yes? Okay. Otherwise, it will get confused. Okay. And also think about it this way. See, if the initial data, so at t equals to 0, see, at t equals to 0, u of x, y 0. So think about it. At when you are starting the AC, so let's say this is 35 degrees. Okay. Now let's say at t equals to just 1 second. So 1 by 360, 3600. So t very small, very small. I'm just taking something. Then I want to see what is the temperature distribution at the exact same point. I'm not changing the point, but at that time. Okay, 3600. I want to see what is it. So you do realize, I mean, whatever you are, it is doing AC or whatever it is, it will take some time to cool that point, right? Yeah, it will suddenly not jump from 35 to 16 degrees in just a matter of seconds. It can't happen, right? I mean, of course, it can maybe in some cases, but generally speaking, practically, it is not very feasible. So basically, you see, for small change in time, you see, you are changing time a little bit. You also expect the answer to change a little bit. So basically, for a small time, maybe a little 34.6 or something, 34.5 or 7 degree, it became, right? So you expect something like this to happen, that for small change in that time, the temperature also changes a little bit, right? So that is the thing. Small change in data, the solution changes proportionally. Conversely, you can also think of it like this. Let's say at t equals to 0, this is the time. T equals to 0, this is place, the temperature is 35 degree. Okay. And the thing is this, you want to see the temperature at a, I mean, see, initially everywhere it is 35 degrees, right? So basically u of x1, let's say this is a point x1, y1 and 0, this is 35. Okay. And there is another point u of x2, y2, 0. Again, it is 35. So everywhere initially it is just 35 degrees. Now the thing is this, after some time, see u of x1, y1, and let's say time is maybe 1 second. 1 second. So let's say this is 34.7. Okay. Now you see, if x1 and y1 and x2 and y2, so let's say this is x1, y1 and this is x2, y2, these 2 points. See, if these 2 points are very close to each other, you will expect that the temperature difference after some time will also be, so basically u of x2, y2 after 1 second. This will also be very, very close to 7.5 maybe. Yeah, very close to this one. You understand what I'm trying to say? It cannot happen that suddenly very two close points will have drastic difference in temperature. That cannot happen, right? I mean, generally speaking. So you see, for small change in data, the solution should also change proportionately. Okay. So if those three conditions are satisfied, we call that PD as a well-posed PD. I hope this is clear now. Yes. Okay. So that's an well-posed PD. Okay, now we want to talk about something a little different. You see, the PD examples which I gave are all linear PDs. What is a linear PD? So let's talk about a linearity of a PD. Linearity of a PD. Okay, see, if the equation f of x u ux, maybe I can put it this way, sorry, f of x, y, u, ux and uy. This is the equation we are talking about, right? This equals to 0 is linear PD if it is of the form. So there is a particular form when we call this a linear. What is the form? If the form is this. For some function alpha of xy times ux plus 1 second. Yes, beta of xy times ey alpha beta plus, let's say, gamma of xy times u plus alpha beta gamma delta of xy equals to 0. So essentially, if it looks like this, where alpha, beta, gamma and delta are, let's say, smooth smooth functions, then we call this function, we call this PDE as a linear PDE. Okay, see, the thing is there is no UUX, so basically these terms are not the square or UUX, so basically this has to be linear in U and it has to be linear in UX and UY also. Okay, so the coefficient should not contain any UX or UY. So basically alpha, beta, gamma, delta only depends on x and y. So this is called a linear PDE. And let's say if PD is not linear, we call it a non-linear. Otherwise, we call it a non-linear. Otherwise, we call it a non-linear PD. Non-linear PD. Okay. So let's start with an example. Let's just understand with an example. Linear PD. Of course, you see all this equation which we have wrote down. You see, you remember ux plus uy equals to 0. You see, in this case, alpha is equals to beta equals to 1 and gamma and delta is 0. So basically, it's a linear PD. Okay, what about this equation? Ux plus uy equals to 0. We talked about this equation, right? If you remember, see, ux plus uy equals to 0. This is so this equation, you see, alpha is alpha of xy. Can it be u? No. So this is not a linear equation. Not a linear equation. So what do we call this sort of equation? For now, see, there is another name of this equation. Okay, it's called a quasi-linear equation, but don't worry about it right now. Basically, it's a non-linear equation, not a linear equation. We will call it a non-linear equation for this course. Okay, another very famous example of a non-linear equation, we can talk about the Jacobians and all, but for now let's just do it like this. See, let's say ux square plus uy square equals to 0. Okay, so you do realize, see, this is not in form. See, this is not in this form. So basically this is a non-linear equation. This is actually a truly non-linear equation, but for now we just call it a non-linear PD. Is it okay? So this is an example of linear PD or non-linear PD. Of course, if you are putting a 5 here, still it is non-linear. Okay, let's say put a 9 here, it's still non-linear, doesn't matter. Okay, so all of these are still it is linear. Yeah, so this is a linear PD. Linear PD, but these two examples are non-linear PD. Okay, now one question before I end this video. The question is, give 3 linear PD. Okay, A, and 3 non-linear PD. Okay, and what sort of linear and non-linear PD? Both this question has to be second order. Okay, do it for a second order linear and non-linear PD. Okay, hint, we have already talked about some linear PD second order. Yes, these are all linear PDs second order. Okay, so this is a hint, but you have to figure it out yourself. First of all, figure out how does a second order linear PD looks like in this form. This is a general form. Yeah, so first of all, figure out what is the general form of a second order linear PD. Give 3 examples and then construct 3 more examples of a non-linear. So that's the question. Okay, so with this I am going to end this video. Thank you so much.